Welcome to the 21st lecture in general topology. The topics that we will explore in this lecture include homeomorphisms and topological invariants. So we'll start with one of the exercises from the previous lecture. So consider our rho, the countably infinite product of the real line with itself, with the box topology, and let the function f from the real line into our rho be defined by f of x is the j-tuple, all of whose coordinates are equal to x. Then the jth coordinate function f sub j, mapping the real line into itself, is the identity function which is continuous. That is, each coordinate function of the function f, mapping the real line into our rho, is continuous. However, the set B, which is the countably infinite product of intervals of the form -1 over j to 1 over j, is a basis element in the box topology on our rho, such that the inverse image of the set B is the inverse image of the countably infinite product of intervals of the form -1 over j to 1 over j, which in turn is the countably infinite intersection of inverse images under the jth coordinate function of the intervals of the form -1 over j to 1 over j. And since each coordinate function is the identity function, this is the countably infinite intersection of the open intervals of the form -1 over j to 1 over j, which is the singleton containing 0, which is not open in the real line, and hence the function f, mapping the real line into our rho, is not continuous. Now recall that for the product topology, a function is continuous if and only if each of its coordinate functions are continuous. And so this example suggests that the box topology is not homeomorphic to the product topology for infinite products. However, it does not demonstrate it. In this lecture, we will officially develop the tools that will allow us to determine whether two spaces are or are not homeomorphic. So, new definition: a topological invariant or topological property is a property that is preserved by homeomorphisms So if two spaces are homeomorphic, then whatever topological properties one of the spaces has, the other space also has. Equivalently, if two spaces have different topological properties, then they cannot be homeomorphic. Now, a topological property is one which can be expressed in terms of points and sets So the second exercise from the previous lecture we will prove as a lemma. Let the space X together with the topology tau be homeomorphic to the space Y with the topology mu. Then the cardinality of the underlying set X is equal to the cardinality of the underlying set Y, and the cardinality of the topology tau is equal to the cardinality of the topology mu. So proof. Now, since the space X is homeomorphic to the space Y, there exists a homeomorphism which we will call F, mapping X into Y. That is, the function F is a bijection for which the function F and its inverse are both continuous. Now, since the function F is a bijection, we have that for every point Y in the space Y, there exists exactly one point X in the space X, such that Y is equal to F of X. and hence the cardinality of the set X is equal to the cardinality of the set Y. Now let U be open in the space X. Then, since the inverse of the function f is continuous, the direct image of the set U is open in the space Y. Conversely, let f of U be open in the space Y. Then, since the function f is continuous, we have that the inverse image of the direct image of the set U, which since the function f is a bijection, this is the set U, is open in the space Y, in the space X. That is, a set U is open in the space X if and only if the direct image of U is open in the space Y. Further, since the function f is a bijection, for every set V that is open in the space Y, there exists exactly one set U that is open in the space X, such that V is the direct image of the set U, and hence the cardinality of the topology tau is equal to the cardinality of the topology mu. So if two spaces are homeomorphic, then their underlying sets have the same cardinality, and their topologies have the same cardinality. So we'll use this lemma to prove a theorem. Let the function f from the space X together with the topology tau into the space Y with the topology mu be a homeomorphism. And let the collection script B be a basis for the topology tau. Then the collection script C, which contains the elements f of B, where B is an element in the collection script B, is a basis for the topology mu. So proof. Let V be open in the space Y. Then, since the space X is homeomorphic to the space Y, there exists exactly one set U open in the space X such that V is the direct image of the set U. Now, as the collection script B is a basis for the topology tau, the set U is a union of some elements in the collection script B. And so the set V is the direct image of the union of the elements B sub I, which is the union of the direct images of the elements b sub I, that is, the set V is a union of some elements in the collection script C which contains open sets in the space Y, since the function f is, since the inverse of the function f is continuous, and hence the collection script C is a basis for the topology mu. So as a corollary, once again, let the space X with the topology tau be homeomorphic to the space Y with the topology mu if the space X is second countable, then so is the space Y. If the space X is first countable, then so is the space Y. And if the space X is separable, then so is the space Y. So proof. Since the space X is homeomorphic to the space Y, there exists a homeomorphism which we will call F, mapping X into Y. So let X be second countable, then there exists a countable basis which we'll call script B for the topology tau. And so the collection script C, containing the elements f of B, where B is an element in the collection script B, is a countable basis for the topology mu, and hence the space Y is second countable. So now let the space X be first countable. Then there exists a countable neighborhood basis script B sub X at the point X for every point in the space X. Now once again, since the function f is a bijection, for every point y in the space Y, there exists exactly one point x in the space X such that y is equal to f of x. So the collection script C sub Y of all elements f of B, where B is an element in the neighborhood basis script B sub X, is a countable neighborhood basis at the point y, and this is true for every point y in the space y, and hence the space y is first countable.